Well, today's lecture should be 3 lectures. We're taking on some stuff that really would be in a second semester, but I thought it would be really important to see it since it connects with the cone mechanics that you guys are doing. And as I've said a couple of times already, there are really two main kinds of resonance, and these are listed right here, and we're going to look at that first. That's this beginning stuff here, where we introduce nonlinear multiplicative parametric resonance as opposed to the linear additive one that we've already studied at the beginning of Unit 4 here. And this is where you get to really, I think, understand where the power for the trebuchet comes from. So that's one thing we want to tie into this discussion. And that will be obvious when we do the animations of parametric resonance. And also, you should be aware the Schrodinger equation is a problem in parametric resonance. And I'll explain that as clearly as I can. So we'll be having motions of a pendulum that's being jerked up and down, analogous, and it's somewhat of a stretched analogy with electronic band theory, which is a favorite topic in this department since we do a lot of condensed matter studies. So the basic idea here is that so far when we talk about resonance, for example, an oscillating electric field applied to our cyclotron orbit, that would be something that connects rather directly to what we're talking about here. We put the oscillating field as an input on the right-hand side of the equation as the force that would go with the acceleration, or ma, if I took the m out of all of this, I've set to 1 here in this case. And then this is the restoring force that we know and love. And it has a parameter, the restoring force has a parameter k. This is kx, right? So that's the situation. Without any friction or damping. We won't bring in friction or damping, but it would make the problem quite a bit more complicated, as we'll see. And you don't have it in the quantum mechanics that is analogous to what we're talking about here. What we're talking about now in the nonlinear or multiplicative resonance, as opposed to the additive, this is on the other side and adds and causes a linear increase in the amplitude that we studied very nicely by making an Archimedean spiral, right, that grew each time by the DC response. And it's very different for this one. It explodes. It's absolutely amazing when you understand it as clearly as I hope we get today. And so instead of having it here, this cosine stimulus, we put it right here to multiply by the x. And that means you're going to very often be having not just exponential behavior, but super exponential behavior, because this thing may be increasing as well. So that's what we want to study today. It deserves more than just the few minutes we're going to do today, as you can see as we go into it. But it is, I think, one of the more important parts of the whole theory of resonance, certainly quantum resonance. So we're going to make the analogy of this with a pendulum that's being stimulated, okay? Now the X-stimulated pendulum, that's what we've studied already. And basically what you're doing here is you're just shifting the thing back and forth in the direction perpendicular to the gravity field. But here, by jerking it up and down, you're changing the gravity field for whoever's riding on this little cart here. Okay? So when you add some extra acceleration to the gravity that was already there for the pendulum equation, you're doing parametric resonance, because you're increasing and reducing varying the parameter, the main parameter, the spring constant. Okay? So that's what's going to make everything go crazy here. And it's also what makes it go crazy in a Schrodinger equation, where you know you have exponential solutions, right? Those are usually called evanescent, and they're dying exponentials, but looked at the other way, they're exploding exponentials, right? We're going to be looking at it the other way very often here, but we're also interested in the decaying ones as well. So we've already seen this one. Let's look at this one, and that's very much the case here. Now, to make things even more complicated, I have what's called the nasty equation, and that's where they're both acting at once. And that's what we started with the trebuchet. Trebuchet is a nasty equation. Okay? That I think is very important. Now, as I say, it's a device we hope to build. But already, if you go to some tourist places in Arkansas, you can get something called the Arkansas Whirler, which is a parametric amplifier. How many people have seen the Arkansas Whirligig or anything like that? Have you ever run into this thing? It's a stick. It's got grooves in it. Okay. Have you ever seen it, Bill? And it's got a little nail here that when you go with your stick, the nail jerks up and down, basically jerking a pendulum up and down. And if you pinch it tightly with a finger, there's a little trick to running this thing. You do it, and then you hand it to somebody, see if you can do it, and they can't do it, right? Main trick is to have one finger really tight on the thing, and then you stroke it. Okay, the wheel just takes off. Okay, so that's right, to bring things down to the lowest levels. That's the simplest parametric amplifier I can think of. But we'd like to build one that does the nasty equation. So someday we'll do that. But right now we have some nice simulations of what this is. Let's do the algebra first here. And what I'm doing is making an analogous relationship from the Schrodinger equation, here simplified quite a bit, no h bars, it scaled it all out, so that it's just a differential equation with a variable parameter. But we know what that parameter is in the Schrodinger equations. It's the supposed eigenvalue of the wave function you're looking for minus the potential being a function of the independent variable x. So with a periodic potential, which is what we're going to make the analogy work for, with a periodic potential, as you would have in a solid, just a simple one would be the so-called Matthew equation, which is just a single cosine. We're going to do the same thing, but now you see it's an equation involving time. That's what makes this thing powerful. And mathematics is the same, except this is x and this is time, but we have to marry or match these various parameters here to the ones that are on this side of the equation to understand the analogy perfectly. So we're going to be on a periodic roller coaster where the roller coaster is being jerked up, the whole track is being jerked up and down and causing us to, well, as you'll see, accelerate sometimes tremendously. Okay, so what we're really doing here is making a marriage between the potential of x and the acceleration as a function of time. And that's just something that's going to be changing the gravity, basically. So we're going to be looking at something that's really quite simple when you just write it this way, and that is the parameter that would be there without the acceleration, the g over L, that gives us the square root of g over L frequency for a pendulum. The pendulum is going to be jerked up and down in the y direction to make this crazy stuff happen. So we have a coefficient of the cosine here, we have a coefficient of the cosine here. These two have to be put together. But more than that, we also have to include what we call the energy eigenvalue in the Schrodinger equation with just plain old gravity over the length of the pendulum to the thing. So the connection relations that we're going to be making will involve that. But first of all, we'll be putting nx, and this is a cosine of nx. That means it's cosine of some potential that has n wiggles in, well, we'll imagine it wrapped around in a ring. So that will then be married to something that we're going to demand has periodicity in time, and that omega y there will be the parameter that marries to the parameter that we don't really think about much when we talk about crystals, but you should think about it, and that'll be the study of that sort of thing will be the topic of the rest of this lecture after we get done with this one. In any case, here are the differentials, and they're the squared differentials. And of course, that's what we have. These are both second-order equations in the independent variable that they own. So to make things simple, we're going to let the n be 2. In other words, we're just going to imagine we have a double-weld Schrodinger potential. And the reason for this is that once you do that particular Schrodinger equation, you have the band edges for the energy bands, allowed and forbidden bands of the most elementary solid state Schrodinger problem. Here it's similar, except we're going to use that n equal 2 to simplify things, and that means I'm already here getting ready to take dt squared with this quantity, and that's where it ends up there. I multiplied it out, but we're also going to have this thing equal to 2, but let's just keep it to be anything for the time being, so we get some feeling for the continuum is possible with both of these equations. Okay, so this guy right here, getting married to that guy, that's pretty important. Okay, and you see, got this multiplying it. So far, so good? Okay, well, we got that other step to make here, and that is what are the potential? What is the thing that actually multiplies that? And I'm going to get rid of the omega y squared by doing that. Here we're going to have this VO just be 4, that's n squared for what we will use, times the acceleration amplitude divided by the length of the pendulum. Okay, well, that's pretty much the algebra, except now I'm going ahead and put in n equal 2, and just to make the algebra simple, let's use a unit pendulum, whatever that unit will be, obviously nanometers if you're talking quantum mechanics, but that is not really an issue here. Okay, so here's what you start with, and this is pretty obvious, certainly, that the classical problem starts with just the pendulum and nobody jerking on it. So whatever that pendulum's omega is, in this case it's square root of g over L, write it down. And then if you have a ring say x that goes around the circumference of a ring, here's your most elementary Schrodinger equation telling you to get the Bohr orbit, the very simplest model of Bohr orbitals working here for a wave function phi. Okay, so this one's got space, this one's got time, but other than that, they're the same equation, and they have the same exponential solutions, exponential cosine solutions. We're going to use the exponentials just because, well, we had a chapter 10 in the introduction that went into this pretty well, so it shouldn't be a problem. And we also have periodic boundary conditions, say between 0 and L, which would be the circumference of the ring, or just a size of a box. I prefer the ring because I want to be able to have moving waves. And e to the ikl, it would be the wave function that had to be 1 after you've gone a full thing with a k equal 2 pi integer over L. So these are the equations that you should be familiar with just from sophomore quantum mechanics. And then here is this guy, where phi now is the actual angle of a pendulum. Okay, that's the thing married to the wave function there. Okay. And again, this is a requirement that we're putting in now just to make it so that it really is like the band theory. I want this thing to be perfectly. I want periodic motion to come out of this monster that we're going to build here that accelerates the parameters. Accelerative parameters are, as you'll see, quite deadly. Okay? So let's just look at the Schrodinger equation. We have solutions for energy values at k squared. K is an integer. 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, and so forth. So the frequencies between those are going up quadratically, or I should say the difference frequencies are going up linearly. And this is the guy that we're solving. Now, I'm using just standard notation here. This is sort of the operator equation. And I am interested in different k values. The operator here, that's the energy operator, is the thing that's giving me my quantum eigenvalue problem. Okay? And believe it or not, that's what we need over here. So what we're going to do is go ahead and say, what is the value of the matrix of this V, which will be translated into the matrix of the acceleration coefficient, the parameter of that one. So I'm just going ahead and writing the V, which is a cosine. And cosine is also an exponential, so I end up here with a very simple integral of just exponentials. I only have to sort the various things into a single exponent. And then I discover I have two kinds of things here. I have k plus n and I have k minus n as my values. And remember that n is going to be 2 eventually, but right now that could be anything. Okay, so I want to move all this up and just look at what we get for a matrix. It's as simple as that. That's the, we call it the Hamiltonian matrix. If you think of a Hamiltonian operator in the quantum mechanical setting, which is what we've got here on the left side of this. So what we'll have are matrix eigenvalues. First of all, the diagonal, and we'll have plus and minus. Start with a plus and minus 1 squared plus, plus and minus 1, but it's squared, so you just get positive values. 1 squared, 1 squared, 3 squared, 3 squared, 5 squared, 5 squared. So I'm separating these things out for the antisymmetric or odd solutions, and then on this side are the symmetric or even solutions, ones that have even number of wrinkles, so to speak, in the wave. And here we're putting that parameter relationship together now. The V0 here of our Schrodinger equation is 4 times the acceleration coefficient in the parametric resonance equation, the pendulum equation, divided by the pendulum length here. Okay, now remember, we're going to set L equal to 1 and N equal to 2. So this guy right here, the potential, is just the acceleration amplitude with a 2 on it. Okay, if I take the 2 through this, I've got a 4 on it. Right. And that's pretty much it. That's all you have. Now, how do you handle what is really an infinite matrix? And the way you handle an infinite matrix is you simply look at, well, first of all, I look at a little 3 by 3 matrix right here, and just ignore the rest of it, because these energies are quite a distance. This 4 squared is 16. That's a long way from 4, so the effect of these drops off radically, exponentially. So you can start to get an approximate solution just by putting that thing in a computer program to diagonalize it. Of course, you can diagonalize the whole thing, but you'll have a mess to start with. You won't be able to sort it out. And then this one's really easy to solve right there. Okay, just got this off-diagonal element, which is that a value for the potential. It's this number right here, the acceleration amplitude. Okay. Well, what happens when you do this? Okay, here are some examples of the eigenvalues for the various quantum states, if you were doing the quantum mechanics and labeling the way we do in good symmetry analysis. And here's a VO0 for 0.2, and that's nu, the coefficient that well, I forget where we wrote it, but it's just essentially this thing with the difference in the factor of 2. And then if you go ahead and consider 10 times that, Okay, here nu is now 1.0 instead of 1/10. You start noticing that the higher you make this thing, the more negative eigenvalues you get, negative energies that would be below zero. And there's a great big difference for having that minus sign in the classical thing we're doing here that you wouldn't even worry about if you were doing the quantum mechanics. Who cares about energy being negative? It's just a frequency that is going to combine with some other eigenvalues, so you don't care where your origin is, and you can make your eigenvalues be all negative by putting your origin up here, or all positive by putting your origin down here. Doesn't make sense to do that for this one. So that is going to be one major difference between these two sides of this analogy. In any case, as you go and look at, well, these are basically, this is one with V0 equal to 2.0 instead of 1.0. You can see here the actual values that we would normally have just plugged into the simulation that we're about to show. So I won't talk about those too much right now, but I will go ahead and just show you what the eigenvalues look like, okay? And the idea is that as you crank up the value of the V0, which is proportional to the acceleration that's jerking this pendulum up and down, you start to notice that the bands, this one drops below the axis. Any of these states below the axis, say right here, okay, and there are two of them that we know of for our n equal to 2. So you change n value, you start to fill up the stuff inside there and make it into a band of different eigenstates for the quantum mechanical problem, but of different mechanical modes for this problem, okay? And we'll look at some of those. But before we do that, I want to notice that there's a huge gap here. And there's particularly a gap right here above the origin that involves, and everything above the origin is a mode that involves a pendulum that's hanging. These guys, as I said, are completely different. They involve a pendulum that's upside down and stable. That's weird. I mean, this is as weird as somebody on a unicycle. How does a unicycle operator balance himself? What is going on to do that? And what he's doing is going just the right, he sort of pumps a little bit, just the right frequency to keep yourself in the stability region. The white region is explode. When it's up here, explode, okay? But these bands here, the allowed bands, as they call them in quantum mechanics, where you have non-exponential solutions, that is, solutions that are confined, you see, to the thing, and periodic as they all are, okay? Those are what we call stable. So when I jerk this pendulum to the frequencies corresponding to this here, it's going to continue hanging, but it'll be doing some very precise motion that will mimic a wave function for the allowed band. Now, we don't even look at the exploding bands in solid state physics very much. We should, because if that's what you're going to get if you start transmitting through there, those are the places where you can transmit most easily. In any case, this as I say, unstable resonance gap, and then another one here is analogous to the gap regions of band theory. Yeah.
So they're all acting as independent oscillator at different levels, right?
Yes.
So
right now, with n equal 2, we're confined to these red lines. Okay, remember I said we picked that n value to be 2. So we're talking about 2 wells, a band theory made out of just 2 wells, not infinite number.
So in consecutive wells, if the particle is at this level and it jumps to that level, right? So this equilibrium point kind of shifts.
When you say jump, already you're talking about a transition in quantum mechanics. I'm just talking about the stage before we transist. Okay? I mean, that's not going to happen in the classical. You're going to be stuck on, you know, one of these things for the analogy of that thing. Okay? So keep that in mind. That's why the sign makes a big difference now. When we're down here, you're stuck with this motion. For every one of these, as you crank up the amplitude, you just get more and more tight here. It becomes more and more persnickety about what frequency you have. But it remains stable upside down. Okay, well, let's just look at something that's in the middle of a gap somewhere, just for the heck of it. That is going to require me to go over to this screen here and bring us up to speed. And that's where we are, more or less. Here are some samples, and the first sample I'm going to take is going to be one that's just out in the jungle here someplace. Now, it's going to be up here, so I'm just going to be looking at this thing as a pendulum. It's being jerked, and it's a normal pendulum that hangs, not does that. Okay, we'll do that in a short period here. But let's just look at this, just to get a feeling for what happens if I have a jerked pendulum in the gap. In other words, my frequency is going to cause the thing to go crazy. So you do not ride a unicycle by jerking with this frequency. And by the way, you shouldn't ride a unicycle at all. You learn to ride a unicycle when you're 6 years old, and it doesn't hurt as much to fall. And boy, do you fall. I mean, I tried to learn it, and I almost killed myself. Most places won't sell you a unicycle. They're so dangerous. Okay? But anyway, this is what happens usually. It just takes off. Now remember, one of the things that we're doing here is we're basically replacing the wave function phi with sine of phi. Okay? Now sine of phi and phi are pretty much the same if you're around 0 and if you're around pi. So this model only works for small amplitude precisely. The resonance is true. Quantum mechanics doesn't do that. It just takes off on an exponential. End of story. This one behaves like a trebuchet. You can see every once in a while it really gets a good shot at it. This is the parametric amplification that makes the trebuchet and all of its analogs, all sports, lever sports. That's where it is. And we're talking about parametric amplification. You got to figure out in golf how to parametrically amplify if you want to hit a long drive and not be taking steroids to do it. Okay, so let's go ahead and pause this one for a little bit, and we'll come over here and we'll take on some of the other examples. I would like to consider a few examples that are sort of in this region right here. I'm going to do the hanging ones first. So let me go ahead and advance this page here. These are the parameters now we're actually using. And I'll take this first one here, a simulation of it, just to show you. This is a hanging one that's very stable. And the period is just right, and this would be slow motion on a unicycle. But you see the wave function we're getting is doing what a wave function would do in a potential that's cosine. Okay? And you ought to play with this thing. And you can go and reset this thing on the other side. Okay? Well, that's pretty much the same. I just gave it a smaller amplitude. But I can grab this thing, literally, and take it over here, pretty good amplitude. And it's pretty stable. Okay, now it isn't conforming to the cosine very well, although it's not doing too bad a job there. Okay, and I can start it over here and make it have a big amplitude that's negative. Even that doesn't blow up like that other one did. Okay, so we're definitely in a stable band right now. Okay. Now, if I give it too much, then the sine phi equal approximation is way off, and we're talking about different problems. But With this one, it's still stable. Okay, still pretty stable. Now you don't know, when you start seeing it doing that, it might go bad after a while, but it turns out that this one doesn't. Okay, so let's reset. Now I'm going to, pause. Now what I'll do is go back there and pick up the next one on the list. And this one's kind of funny. This one it's still a hanging mode, but it's a nice one. Oh, that's the same darn one. Let's go back here and see what it is I did wrong. Pause a second here. Jupe. This is the one I was trying for. Let's see if I get it. No.
It's the same omega.
Same old darn one, right? Let's see if I can do it from here. This is, well, we'll just see what we get when we get that one. That is the third one. There, you see it's making a very nice wave with a flat top in the region where it's there. And also very stable. Okay. And very well behaved. I call this one the unicycle mode. This is one that you could really count on if you ever learned it while you're doing it. But don't try it at home, okay? All right? Okay, so let's pause this one and go on and see if I can get some of the other ones to work here that we have. I guess the one that I should go for right now is this guy right here. Let's do this one just for the sake of argument. Yep. Now I really am talking about a unicycle upside down. Okay, so this one really is quite stable upside down. I can get it to go ahead. I can get it from the other side. So I can have a plus wave function or a minus wave function, and you see them conforming to the potential very nicely. And that's what is required in some sense for every one of the states we're talking about in order to be stable, particularly upside down like this, where you have negative energy. This one is about to go though. And that's mostly due to sine theta not being theta. It found a doorway and went crazy. Okay? So now it's trebucheting. Illegally, I might add. But who cares about legality when if you don't follow the rules perfectly with this, as I say, you fall and go visit the hospital. Okay, let's try one more here. This is just that original one. Let's go back and pick up another upside. We only have two of them because they're the two sides of the band that we're looking at right now. And this probably would be a good one to look for as a unicycle driver, because you can see it brings you in to the center. Okay, it centers you. It's a whole nonlinear effect, but it centers you linearly. Okay, so that means you really have to learn the motion, otherwise you're off on the hinterlands. And you can have a pretty good amplitude here too. But as you can see, the sine theta not equal to theta is giving me a very different wave function than the quantum mechanics would be for this. But it's still stable. Isn't that amazing? This is a side of I should say, parametric resonance theory in general that's not taught. It should be taught early on. It's beautiful and simple. And you have calculators that give you eigenvalues, so you can do a whole bunch of things that are more complicated with it. Okay? So I hold this up to you as a thing worth looking at. Okay. If there's anything else I need to say about this that isn't too out of the realm here, but anyway, what we just looked at were these two right here. One of them very close to the zero. there was one, there's the other. Now, you can do a lot more with this. Suppose that instead of having this nice cosine motion, you just jerk the heck out of it. And you stay there for a while. And stay there for a while. There. Then you've got the square wave Kronig-Penny model of band theory. Okay, and this comes out of Chapter 14, Unit 5 of our quantum mechanics course, the one that I haven't given for a really long time here. And these bands cross. There's all kinds of weird stuff going on when you have a lot of Fourier components in your potential, enough to make a square potential in particular. So that's worth noting. And then if you're just looking at n equal 2, remember, you just get the outsides of the bands. But if you go n equals 6 and make it periodic in 6, then you look at a lot more states. Instead of just having 2 states, you have 6 of them. Count them. 1, 2 that you already had, and then a doublet here and a doublet here. And we're going to discuss a little bit about that toward the end of the lecture today. So get ready for the cyclic theory of band theory to be coming here shortly. Any questions about this I can answer? Beautiful analogy. And that's what physics is. You make analogies, things that you sort of think you understand, and then you go back and you look at physics and you, wait a minute, I guess I didn't really understand the thing I started with, right? And that's the fun of it, right? Back and forth with analogies. Okay. We're back in, shall we say, I don't know, back in the 50s, okay? We're looking at something that has C2 symmetry. We've already seen this. This is where I did the A, that means A times a unit matrix in this case, which is A plus D over 2. We're leaving that out right now. Plus bilateral symmetry coefficient and the bilaterally symmetric B-type spinner, sigma sub B. Remember that guy? Okay? So I want to go through real quickly this, looking at it using that powerful theory of U2 operators, and introduce you to how the group theory works for big problems like, well, buckyball eventually, but just making it have n equal 3 or n equal 4, which will be what you're being asked to outline in the problems that I'm giving you in the homework for over Thanksgiving. Isn't that nice of me to so you won't feel like you don't have anything to do in Thanksgiving. All right. Anyway, here is the K matrix, which is that's H squared, and you worked a homework problem that centered on that idea. But in any case, either one of these is subject to the symmetry things. And either one of these has a Hamiltonian that's gotten by just looking at the group multiplication table. So that's the name of the game here, is to really take seriously the bookkeeping that's provided by group theory just at its multiplicative level. So we already worked out the modes that you get by combining this state with this state, either the plus sign, that was a symmetric mode, or a minus sign. Well, the group theory tells you to do that, and that's what I want to show real quickly here, just to get this off the ground. And all of it is based on the minimal equations of the group elements. That's the key thing. Looking for the minimal equations of every group element, or a select few group elements, it turns out. If you had to do it for all, it wouldn't be very powerful. So here we got sigma squared equal to 1. That means sigma is equal to plus or minus 1 something. Okay, there's a sigma plus 1 and a sigma minus 1. That's the Hamilton-Cayley equation, giving us a 0 there. Sigma squared minus 1 factor. Okay? So there's your two projection operators, except it's little p's. They're not been normalized yet. Remember, we have to normalize projectors. Well, that's also done automatically by the group. So there are a whole bunch of things here that use the theory of matrix diagonalization that I presented to you as a powerful projection method, fine if you don't have any basis for understanding the symmetry of the matrix, but if the symmetry, then you reduce the symmetry, not necessarily the matrix itself. That happens automatically. So we do have a factor of 2 that you would know there. That involves the difference between the eigenvalues 1 and -1 with either a plus or a minus sign. So those are the projection operators that give us a symmetric mode, which is usually the low frequency mode, and then there's the usually higher frequency mode where they're fighting each other. Here they're just sort of going along with each other. And that was true for our pendulums that swung this way when we made this real live demonstration of our coupled oscillators with 2 pendulums. Now what we would really love to do is get a ring of these things with 3, 4, 5, 6 pendulums so you could really see the band theory that goes with this in group theoretical terms. That's yet a dream yet to come, but we can still do it on paper or using photons on screens to get it. So this is just the application of the projection operator to the, well, here's another thing. We name these states using the generalization of Boolean algebra. So it's going to be a qubit eventually, but we have 0 and 1, okay, as our bits, so to speak. Now, we normally would call this one x and this one y and plot the thing in x and y coordinates, or we would call this one 2 modulo 2, which is 0 modulo 2, and this one -1 maybe. All kinds of different names that you could give it, but the idea is that the group elements name the various states. That makes a lot of sense when you get done. In any case, this is something called a group character table. How many people have ever had to work with those things? Did you do it in your algebra class at all?
Not like
This is what the physicists have done with group theory, is they simply have given you a table with the numbers that are the eigenvalues of each of these group operators in an abstract sense. Symmetric and anti-symmetric. Well, I call it 0 mod 2, 0 bit, and 1 mod 2, 1 bit. Okay? And then the m's here are called wave numbers. This will make more sense when we go to 3 next. But P for point, there are 2 points here, point 0, point 1, okay, of coordinates, as position. P for position, M for momentum. That sounds silly at this point, it's such a simple thing. But then, actually what we have here are 2 phasors. Phasors lined up in phase, phasors that are out of phase. Those are our 2 modes. Wave modes, M for mode, okay. Trying to find as many mnemonics as I can possibly find, okay? To the point where finally you forget the mnemonics because there are too many of them, but bear with us. Okay, so I want to do C3 this way, all right? Here's the product table for C3, okay? And what's neat is that all you have to do to build a matrix that represents, say, R1, okay? Well, 1 first is very easy. There's a 1, there's a 1, there's a 1, so you put an actual numerical 1 there, there, and there. But then, for R to the first power, not to the 0th power, but to the first power, I have, okay, in this table here, I got R1 here, so I put a 1 here in a matrix to represent it, 0 everywhere in that row, and then I go down here, I put a 1 down there, and 0 there, because it's not R1, and finally this guy in the corner here gets a 1 in the corner. So there's R to the first power. Now if you square that, you get this one, but you can see it from the table that R squared has 1s there, there, and there. What could be simpler? That's our Hamiltonian. We've just got the Hamiltonian right from the group table. Not only that, but this group table knows its eigenvectors. You just have to ask the group where are the projectors. You have to ask nicely. But that's the way it tells you the eigenvectors. And then the eigenvalues also follow very directly just from this. So this is a direct route from something that's considered very mathematical to something that is very physical. That is, the modes that we're going to make out of these base states. These are the base states. Okay, base state where number 0, where mass number 0 has moved out to a unit position. That's a classical thing, but we're using quantum mechanical notation for it. And then this one right here. These guys are quiet, nothing going on there. But the middle guy, this guy right here, number 1, which is the second one, if you're counting this one as the first, so the first power right here is this guy. He's got a unit displacement, everybody else is at home. And then this one gets a unit displacement, that's the third unit base. Okay. So it's linear combinations of those that are going to be modes for this system. And if this system is 3 potential wells with wave function that we're trying to find, it will be that too. We're going to take care of a lot of different physics problems at once here. All by working with operators, and all the operators here that are doing anything are the first power and are the second power. This doesn't do anything. It's the identity. So we just take linear combinations of those guys, not leaving out the identity, but the basic idea is to spectrally resolve the group table, which is the Hamiltonian, or the K-matrix. The K-matrix will just be this thing squared. So pretty soon we get there. Now, here's our minimal equation. R cubed, and this is true of all the R's, okay? All powers of the R go to 1 if you do it 3 times. So 0 equal R cubed minus 1. So what we need are the cube roots of minus 1. How many of them are there? There are 3 of them for each of the values of m. M, it's called multiplicity or something like that. Okay, but we're going to call it momentum very shortly here. So in the complex plane, here are the 3 complex numbers that represent the roots of unity. And that is the beginning of all of this spectral decomposition for cyclic groups in general, but this is the first non-trivial one. Okay? So we know that it's going to spectrally decompose these elements, and the values associated with them, we already know their eigenvalues. Okay? So here's the combination of 1r and r squared in terms of the projection operators we are about to calculate. But we know they're there because of what we've been talking about in linear algebra of matrices. So it's easy to resolve this. Now, what makes it easy? The fact is that we've got the kets here. These are the bras. And the coefficients of the bras are what we want for the projection operators in terms of the group elements. The kets just take the complex gun and transpose them into columns. That's what we're getting here, these numbers in those places. And just remember what those numbers are. Rho m is e to the I times 2 pi over 3 to the mth power. Okay, now if we're going too fast on this, I don't want to leave you behind. This is something that you should follow. And then I want you, without looking at this, to repeat that on a homework problem. Then I want you to do 4. Okay? It's a Thanksgiving homework. Okay? Then I want you to rotate a surfboard and it's bunga bunga all the way. Okay? Okay. So, here's the answers. Pretty much already out there. Basically, we're going to have 3 phasors all lined up. Then we're going to have 3 phasors, each one moved by 1 step, say, clockwise. And then another one that's been each one moved a step counterclockwise. Done. But going through the algebra gives you these things. Now, where is this most important to physics and engineering? Just go for a drive anywhere in this country, but it's also in Europe, although we're getting to the point where everybody has solar, so you don't need these transmission lines, right? And have you ever noticed the transmission lines have 3 cables? It's 3-phase, right? And you can actually get 3-phase in your house if you want to run something big like a dryer or something, right? And it's much better because you run at higher voltage, because these things are not quite as much voltage difference between them. They're all sort of in between being plus and minus. It's also more efficient to ship it long distances. Okay, so then that question begs, why don't we have 4-phase, 5-phase, and 6-phase, right? Well, you run out of copper. Okay, so that's the character table for this group. And these are the momentum numbers, or mode numbers right here. 0 mod 3, 1 mod 3, 2 mod 3. And that's a very efficient way to list them. And I haven't seen anybody do this. This is what Beta calls this one alpha, beta, gamma. Somebody else calls it gamma 1, gamma 2, gamma 3. Doesn't mean anything. This means something. This is now a 3-bit computer, which we're not familiar with, right? We're always used to 2 bits. Maybe quantum information theory needs to think about that. Why just use what you've been using for the good old-fashioned things we have here that are binary? In any case, this is something to remember for your solid-state physics. The lattice length, actually that's numbered here, we get away from even talking about that using group theory. We're just counting, okay? But the lattice length, which is 3 somethings here, something's A, okay? Lattice spacing is the usual letter used for in textbooks, are related, okay? And if you need to make a wave function, it will be involving the lattice spacing. Here we're just treating it as 1, but be aware that that's not what you'll see when you open a solid state textbook. Have some number of nanometers or angstroms. Okay, so P is the power of the operator, R to the 0th power, R to the 1st power, R to the 2nd power. So the group operators are up here, and then their eigenvalues, their mode numbers, are down there. So power P is the power of that, but it's also the position point P. So there's 3 mnemonics in there, okay? And then the mode momentum, there's 2 M's there, all right? They're just talking about the subscript of that K vector, 2 pi over lambda M, the wavelength, okay? The wavelength is very important, and basically this is a wavelength that takes up the whole ring. This is a wave that has 2 waves in there. That's 2 modulo 3, which is minus 1 modulo 3. That's the arithmetic you have to do. The modular arithmetic is the generalized Boolean algebra of all of this sort of discussion here, whether it's quantum or classical. Okay, so each quantum number follows a modular arithmetic. Sums or products are an integer modulo 3. You always express them that way if you really want to keep track of them. So you can either have 0, 1, or 2, or else you can shift the thing down. This is called centered band, origin-centered band, minus 1, 0, or 1. Fine. It looks more like what we started with, minus 1 and 1, and then we got a guy in the middle there. And now, or you can go down to minus 2, minus 1, or 0, or minus 2,000, minus 1,909, etc. As long as there are sequences of 3 nearby integers. And the idea, of course, is, for example, with m equal 2 and p equal 2, this number right here, this guy right here, you can switch to any of the modular, switch the number in there to anything that's the same thing modulo 3, and it will not affect the wave. That's called Brillouin band jumping in physics. We'll say more about that as we get more complicated examples up here. In any case, this is the C3 arithmetic, basically, up to the point of getting the eigenvalues. Okay. Now I'd like to use the screen over there to show the eigenvalue thing, so we can compare it to what's going on over here. So I'm going to be scooting ahead to the C3 department. And there we are. That's where I want to be. Okay? There are 3 eigenvalues corresponding to 3 roots of unity, and that means there are going to be 3 eigenvectors corresponding to each of those said roots. Okay?
And so to get the eigenvalues, I simply stick my Hamiltonian, which is a linear combination of the group operators, and we know what the irreducible representations, that's a big fancy name for these roots here, these complex numbers e to the I m times the point. This is the point or power. Power equals 0, 1, and 2. Basically, this is like the x-axis, x around the ring of three things. Okay, so I simply substitute in the right values for those roots and the wave functions that go with them. Each one of these guys here is a wave function for a particular m value. M equals 0, 1, and 2. Okay, so we're getting the eigenvalues for all the different values of m right here. And it boils down to just 2. M equals 0 has an eigenvalue of R0 plus the coupling R1. And then there's R0 minus R. That's degenerate. There's 2 states on that single eigenvalue. Okay? So that's the algebra. That's the algebra. All there is to the algebra, just based on these numbers right here. Okay? So the H eigenvalues come out to be, and this is just writing them out in a form here, for each value m, I'm going to be getting something that's a function of my parameters, diagonal and off diagonal are the only two parameters I've got. Symmetry has given me that. Or what I'll have here is the k eigenvalues. They're going to be the same. Eigenvectors and eigenvalues are the same. And remember, one of these matrices is a square of the other. This guy is a square of this one. Right? That still holds. Okay? So the actual frequencies in quantum mechanics, as we've pointed out a number of times now, the actual frequencies are the eigenvalues of this guy or the square root of the eigenvalues of that guy, which are the same as the eigenvalues of this. So you have to put a square root on everything you got in the H matrix in order to get the eigenvalues for the K matrix. Well, that's a big deal because that square root function right there is a dispersion function for phonons. So you're already doing the most elementary excitations in any solid. Just the vibrations. Forget the electrons. Sound cool? Okay? Yeah, it's cool. All right? So, I'll bring both of these up to speed here. I'm going to do that on this screen right here. This color's better. Remember, I use color in a funny kind of way here. I use green for things that are degenerate and capable of motion. Green means moving, as in traffic light is green now, start moving, okay? Whereas this guy's all by his lonely, so he's standing wave. He just sits there, you know, had too much to drink and never moves, right? Okay, and that's true both for the phonons and the excitons. These are basically excitons. We're talking about electrons, very simple excitons, I might add. Okay, and anyway, there's the phonon dispersion right there. That's what it looks like. Take the square root of a cosine, which is what the thing would be for the quantum mechanical solution. And there are the modes. But these are particularly funny modes. These are modes that are made by taking combinations of the degenerate guys. This is a cosine mode right here. It's a standing eigenwave. It's a plus combination of plus and 1, minus 1. So C2 symmetry is coming in here and saying, hey, don't forget about me. I come symmetric and antisymmetric. One's called cosine mod 3 and the other's called sine mod 3. Okay? So they still get the color green though, because all you have to do is stop having this particular combination and they'll move. They'll move like this one, which goes full speed around this way, and this one goes full speed around the other way. But these guys right here are standing waves. And this one is 0, just permanently 0. Moving wave doesn't leave anything permanent. And then this guy's a standing wave, no matter what you do with it. There's nothing combined with it. So does that make sense? Both the physics and the mathematics is analogous again to classical mechanics. You see, this is an example where Totally classical thing. You spring, you don't have that in quantum mechanics. You have funny little tumbling things going on. That's what the springs are. This is what I mean by having a standing wave if it was longitudinal. It would all work again. Same stuff. Okay? All right. We've got enough time to have some fun with this. One of the things we have to do is point out that if you have 6 objects, you've got a lot of choices for Hamiltonians. First of all, you have the one that Bloch uses exclusively. Most solid state books won't draw a coupling between next nearest neighbors like this, but they're there. And then there's a crosstown coupling too, so there's 3 different C3 symmetric Hamiltonians, mutually exclusive as far as coefficients that they use, that occur for C6. C6 is a lot more complicated than C3, but it has C3 as a subgroup. Okay, kind of, there's a hiding C3 structure in there. And then there's a C2 structure, 3 of them, in there. So you have 1 times 3, and then 2 times 3 is 6. You've got 2 of the guys that are coupled, and so that they would really be C3 symmetric and nothing more. And then finally you've got this guy that's coupled all the way around the ring. That's the new guy in town. Okay? So now your eigenvalues are going to be linear combinations of coefficients with different names to them, R, S, and T. Nearest neighbor, next nearest neighbor, and then finally crosstown, T. Third nearest neighbor, which is all the way for this. So here are the C6. This is what you get if you went to the library, got a group theory book, and looked up C6 characters. You'd get this. Isn't that pretty? No, it isn't. This is pretty. These are the phasors describing one wave modulo 6. And there's its imaginary part just drawn in there for the heck of it. It has an imaginary part that is 90 degrees ahead of the real part. Imagination precedes reality by 1/4. That's the rule in most of U.S. corporations, right? Because you got to report to stockholders after a quarter. So you better get the idea working before they come to the meeting. Okay. We have 1 mod 6, and then something that looks just like it that is 5 mod 6. This is a wave that has 5 wrinkles in it. But those wrinkles come out to be a wrinkle of 1 going the other way. You see the wave there that is just got 1 wavelength there, just looking at the arrows on the clocks, right? It's the same as this wave going backwards. So 5 modulo 6 is equal to -1 modulo 6. That's the arithmetic equality that makes this wave related to this one. And this one doesn't have any relatives. So these 2 guys are going to be degenerate in frequency for the normal Hamiltonian. Now, next is 2. I've got 2 waves here, okay, plus the imaginary part, all right? Well, running that one backwards is this guy. That's 2 minus 2 modulo 6 is equal to 4 modulo 6. Okay? So these 2 guys, plus and minus 2 modulo 6, are going to be degenerate. And then there's this guy. There's only 2 colors in here. Red and its opposite, cyan. That's just like kind of this one, which has only 1 color in it, right? So this is a standing wave, and this is too. Because this is the Brillouin band boundary for C6. You've heard of that, haven't you? The Brillouin zone boundary. Okay, if you take any solid state, that's their favorite thing to amaze you with. This is all there is to it, except that it can happen in many dimensions. Okay? Again, this is classical mechanics. We use the same pictures for the actual quantum systems of phonons, magnons, excitons, you name it. polarons, they all use this kind of stuff if you've got a C6 system. And the others use it for some higher than that. Here are the actual eigen modes, I should say eigenvalues written out, okay? And it's interesting to note, you just take a six-sided polygon, and it is showing you, using a cosine, what that is. And this one is the same thing, showing you a two cosine. That's what you'd have as a spectrum if you had this kind of coupling right here. And if you were stupid enough to have a molecule like that, where these things could just rotate with each other, then you'd have this situation. You'd have all of the energy levels up here, and then you have all the other energy levels down there. There's a doubly degenerate plus a singly degenerate guy hiding in there, and the same thing up here. So there's three levels that have been smooshed together by only having that kind of coupling, and that makes sense. Because this thing is just doing its thing independent of this guy and this guy. This pair and this pair and this pair are independent completely, not feeding energy into each other. Whereas here you have a threefold guy feeding energy into another threefold guy, so you come up with this doubling right here. And then the singlets are all making a doublet too. Now that's, you know, all stuff that you can see by eye using this geometry. It's really quite powerful. And then if you want to put a magnetic field on it or rotate the thing, you just take the hexagon of the elementary one and like that, and your whole dispersion function translates. It's called gauge changes. Change of gauge causes this. Now you get Zeeman splitting of the doublets, and the singlets just move to second order, and then finally they go all the way across. If you turn this thing all the way around, you can watch this thing move anywhere. That's, if you want to upset your solid state teacher, tell them about this. Okay. The rest of this is just talking about how this generalizes. And here's a case of C12. It's quite complicated, but let's go for it. Here's C16. Isn't that beautiful? 1 mod 16, and then here's 15 mod 16. They're both country cousins. Okay, it's city cousin, that's country cousin. Okay. Then 2, that's the same as this, except for going backwards. And 3, and then, where, do you see the Brayton zone boundary in there anywhere? Sort of midway. 8 mod 16. Okay. Up, down, up, down, up, down, up, down. That's your Brayton boundary right there, wave function for it. Okay, and it's singlet. There's no doublet with it. All right? You want more? Let's go for 32. Oh, hell, let's go for 64. Oh, let's do it big. 100. Okay? Somewhere in there is 50 mod 100. That's Brayton zone. I can see it. It's right there. This is what an integral transform would look like if you plotted it to the degree of having 100 pixels to play with in each direction. That's, of course, 10,000 pixels to play with to make all of these little phasors. And what you're noticing is that the product of M and P, momentum and point number, okay, or power, product of M and P is a constant on this chart. That's what's making these hyperbolas. Okay? And then there's other things you can see in there that are much more subtle. And they're best seen if we let this thing run its course. Okay? This is 256. We're really doing silly now. It's hard to tell the difference, right? Okay. Now, what I'd like to look at is just quadratic dispersion. So I'm going to jog all my constants so I get quadratic. That's a Bohr dispersion, right? Bohr-Schrödinger dispersion is energy equal k squared. Frequency equal some constant times k squared. That's what we're going to play with now. And I'm going to do it by jockeying these constants, okay? Most band theory has something that's sort of cosine-like when it starts out in the simplest form. And a Bohr dispersion would be a parabola that kisses the bottom of the cosine. So that's what I'm after. I'm going to force these things to have that dispersion. Now, if I'm only going to work with the states at the bottom here, I don't need to do that. But if I'm going to work with all of the states, I do need to do that. And here are the coefficients that let you do that. I won't go into that. That's more advanced than this course deserves. But anyway, we've already talked about how to geometrically plot the beats that occur when I add these two together. Okay? By adding, I mean I add this gray thing to this black thing, and this gray thing to that black thing. Okay? When I do that, I get nothing. So there's the start of this thing with all of the stuff on the x-axis, everything in your polarization things. And then as I let the bottom one turn, I leave this one alone because I'm only interested in the relative phase, this is what happens next. And remember, that was what gave us a circular polarization. That's a quarter wave plate that caused that to happen. Then a half wave plate takes you all the way over to the y-axis in our two-state description, or your probability all the way over to the other side of the whatever that little molecule is. And then you get this guy again, and then you start over. Okay? And you can see all that by geometry, and we've looked at that. So this is the story for C2. Well, C3 has a story too. This is its story being literally plotted out in space and time. What I'm after here are the generalizations of the beats that occur, quarter beat, half beat, three-quarters beat, that make our very interesting states. And they generalize to something called a revival. So you wouldn't talk about revival with just two states. It doesn't make sense. But still, there's this big X for the zeros of the waves if you could plot that sort of thing. And it's a bit of a stretch to even do it, but I'm doing it here just to make a connection. So when we look at the animations of this thing, there's the beat, okay, going on. Because I'm turning this one and not letting that one move. Usually omega equals 0 for k equals 0 is a good student's band theory. And then these guys are the same thing, except they make revivals, beats, if you will, that if I stop that thing at the right place, I see this one, and then I see this one, and then they all pile up on one thing, right, well, not quite there, but anyway, there is a point where there's nothing on the other ones, just like it was for the two. And what I'm going to show you next, this is the problem that you have, or the case that you have for your fourfold oscillators. They make these revivals, very weird combinations of phase when all of them have the same equal amplitude. They all get to show their day in court, so to speak, here. Like, well, there's one that's all piled up there. Then there comes a time when they're all same right there, and so forth. There's one of these things, or one of these things. Okay, and then there are these other revivals that are just like what you get at C2. Okay, this is C5, which has all moving waves, but it still does this, except they're all the same amplitude. But they're weird combinations of phase in space and time. So this is a space-time diagram of waves, which we're going to be talking about at the very end of this course. Here again is C6, showing its wonderful revivals. Okay, and remember, these phasors are all adding up to give the phasor that's up there at the top. So when it all gets to be in one place, they're all lined up on one column there. Stuff to play with on your own. Remember, this is all on the web. Okay. Now, we're going to look at this. This is a continuum where we let a Bohr orbital explode in a Bohr dispersion environment. And we're going to let a lot of phasors have an amplitude, but we're going to taper that amplitude because that's the one that gives the sharpest diagram for this. Anyway, here's a typical threefold moment that we looked at in the character tables. And that means that on this graph, the phase in that smudgy region right there is that. It's the same as the phase in this region. Phase is not indicated here. It's just amplitude, and those white areas are zeros. See the zeros meeting right here, and then another one meeting right there. Okay? And then this guy's completely different. This is real. This is actual real number right there. What's cool about this is that waves not only give you a graph for space and time, but every point on here has a signpost to tell you what the time is. The phase arrangements are all unique for everything on this plot. I don't think very many people appreciate that the waves could do that, but they do. And here we're going to just go ahead and let them run. We're going to let this happen for a lot more states. This is just a 2-level system. There's about a 3 or 4-level system showing its plot in space and time. This one, we're talking about fractional quantum revivals. We're going to make a bunch of things that are associated with the real numbers, the real fractions, the rational fractions that exist between 0 and 1. Something mathematicians talk about but never do anything about. Here it's going to be doing something about it. Okay? And basically we're going to be tracking the location of collisions between a bunch of lines that have rational fractions associated with them. Like this particular one right here is associated with a slope of a half. Looked at from this point of view. This is slope 0 here, looked at from here, or if you look at it from there. But let's look at it with your heads turned sideways. So this is a half, there's a quarter, there's an eighth, and there would be a 16th, and, or a 10th and a 12th there. But you don't see that on this graph. You hardly see even the first one. Quantum mechanics doesn't care about where you are. It cares where you're not. All of these lines that are blue are zeros. And look at, there's a lot of them, and they show very clearly. That is a very important message. It's not so much that you're here in this room. It's what it took to keep you from being anywhere else in the universe. And if you wonder about being Zen, you have a wave function that is everywhere in the universe. It's really tiny. It's interfering itself to death. You're here with life for now. That doesn't last forever. Okay, that's enough philosophy here. We already seen the same diagram with a crash. This, I think I've already shown you where you actually calculate with algebra where the time crossings, the time for crossing, and the angle for crossing. So you can actually work that out. And this is called a Fayetteville sum. I think I mentioned this already. Your students probably do fractions like this, and you mark them wrong. But for this purpose, you mark it right. This is John Ferry's way of keeping track of tides, Bay of Fundy, which has lots of modes. This is the way he found the modes. And this is 1815. Okay, we're talking way back there. Philosophical Magazine, 1816. All right? Now we've got some more modern literature on like Harter, but who the hell is that? We've got Mr. Ford, Les Ford, mathematician, in 38. He's responsible for something we're going to see here that goes with John Ferry. It takes a long time for that to come from that, but, well, let's go for it. So what we're going to see here, and I'm looking now for the, this is just a description of how you make fractions very beautifully. And the basic idea is the Fayetteville sum makes real sense if numerator over denominator is thought of as a vector space where you plot the numerator this way and the denominator this way. So when you add the vector 1, 1, that's 1 over 1, representing that fraction, it's representing 1.0 actually, if it's a real line, or 0, 1 is representing 0.0, right there. You add those two Fayetteville fractions, you get 1, 2, 1/2. So this is a construction to find 1/2, the most elementary, not completely trivial fraction. Okay? That's the basic idea. You just take this arrow, extend it, and it should hit right at 0.5 with a coordinate of 2 versus 1. Okay? And then you draw a line from the center, the 1/2 that you've already gotten, through the intersection to get the next one. And that's the cool geometry here. Circle radius at the intersecting line there, that's, I believe, called a Ford circle. It's a Ford circle for the fraction 1/2. There it is. Okay? Now, have I mentioned the movie this goes with yet? Titanic? Have you seen the movie Titanic? How many people have seen the movie Titanic? Just out of curiosity. Anybody? Really? You missed that. Okay? Well, you're not going to understand why I colored that blue. Go see the movie and then you will. But in any case, the next one is a third. See, I'm fairy summing here. This guy with this guy. Okay? Next, I should be doing 1 plus 2 over 3 plus 3. That's 2 over 6, which is a third. We already got that. But that is still the progress that you make. These are all fairy, a fairy tree. Okay? And there's the fractions all lined up as circles that are tangent to each other. This is really cool. So you've got a kid that you're trying to get interested in mathematics, and they're hating fractions, which every kid does. I think I hated them as badly as anybody. I've seen this. Wow. Wow. And not only that, but the Fayetteville's rectangles give you the fraction. That's something I didn't see in any of the literature that I could find so far. Okay? Now, I am going to quickly here back up and see if I can find where we did the revivals for this. I think that probably the best thing for me to do is just go to CN Wave and let her rip. Let me go ahead and escape here and go to the browser and go to finding Mr. Wave and run that. Okay, so let's go here.
Window up.
I'm looking for bookmarks, and I'm looking for Wave It. There it is. And it makes lots of nice waves like we've been looking at here. It's where most of them were drawn. But what I'm going to do here is I want to go ahead and look at the scenario that's associated with that. And that's way down here in the bottom here. Let's see if I can find it.
The second section from the bottom.
The second from the, that's right here.
Yeah.
Gauss. And I probably want to do the Gaussian because that's the simplest. Let her rip. Okay, so it starts out with a wave all piled. This is what I call the tiny Big Bang. Your universe is a circle. You pile all your matter up in one little pile, which is right here, and it spreads. Everybody knows that Gaussian spreads. But look what happens when it runs into itself going around the other way. That's when you get all the fractions. So this fractal diagram, this fractal for fraction, right, is literally close to its name. It's literally giving you, whenever it's an odd number, it's giving you that number of zeros. Whenever it's an even number, it's giving half that number of zeros. 1/8 gave you 4 little zero areas. Okay? And you can see there what we mean by zero. We mean near zero when we drew there. There's a nice one right there. 1/6, you get 3, which is half of 6 spots. And so forth, you see. And every time you get a number, you get that symmetry up here. So briefly, every symmetry this thing can comprehend, depending on how much energy you've given it, is going to make its appearance at different times. Those times determined by the fairy sum. So this is a key to a whole bunch of other things. Quantum Hall effect, KAM chaos, the root to it. There's a bunch of things that use this arithmetic very deeply. Now you can see where these are all headed. Halftime is right about there. And that's when what started out on the North Pole ends up completely piling up on the South Pole. That's the major revival, which is just a beat. It's a beat. I mean, that's what happens with two things. Two things can do that. But here it's a whole bunch of things, a whole bunch of components. And we have about 14 or 15 components, so those are the first fractions we see. You got to put more energy in this thing if you want to get the fractions denominators up. Isn't that cool? It's scary. And we're getting there. You see them all converging there? It's Christmas time. 1/2. Cool. Let me, I'll just leave it as you leave here. You can see this thing again. I'm going to pause this one. Look at the scenarios again, make sure I've got what I want.
You showed a boxcar one for contrast.
Yeah, that's what I want to do. Let's turn on the, let's go to controls and do that.
Oh, it was at the bottom.
Oh, it was at the bottom?
Yeah, it was in that same section, third
Okay.
boxcar, one up.
Yeah, this guy
Two
right
up.
here, with distribution.
Yeah.
Okay, now, we're skipping something here, but I could have a Fourier distribution that was a boxcar. This is what the experimentalists call this. Look what it produced. It produced sine x over x. It produces a horrible mess. Okay, and they bend a little bit, they have to do all kinds of stuff, because there's such a sudden drop off here that it goes crazy right at the end.
Shock. You need more Fourier components to create.
Anyway, you see all the symmetries up to 15 clearly, but right on top of 14, 13 with the same amplitude. So you get a very confusing pattern here, but it is a very structured thing nevertheless. Take a magnifying glass to it and you see repeats of patterns all over. This whole thing will be covered with stuff like this when we get down here. Okay, so that terminates Unit 4. As they say, this is how the world ends, not with a bang, but a whimper. That's Robert Frost, right? You all should read a little bit of Robert Frost sometime. There's 1/4. It shows up, but it's got all sorts of scars in it. Okay, well, have a really good Thanksgiving.
Okay, thanks.
And we'll see you after that. Assuming I survive.